the key part, which is about what we call the assumptions underlying linear programming. And when we talk about linear programming, basically we are referring to that the linearity can actually hold as a major assumption in linear programming. And when we talk of linearity, here we are referring to that we have got to have two basic variables which we can be able to plot, say on the y-axis as well as the x-axis, so that at the end of the day we'll be able to draw a linear equation. If you remember from our topic number 1, we said that a linear function can only relate two things, that is one to be plotted on the y and another variable to be plotted on the x-axis. So basically, when the number of decision variables goes beyond 2, you cannot be able to have the case of, for example, using the graphical method. So we assume that everything can be illustrated using linear functions, and that is our major element because it's the one now constituting the definition of what we call the linear programming. So these are the basic requirements when it comes to solving a problem in relation to linear programming. Number 1, you have to know, what am I doing? Am I maximizing or am I minimizing? That's the first thing that one has to consider. And basically, this one, if you have to look at what I'm scrolling down, I want to take you to the elements required before you formulate the problem. One is that particular objective. Am I maximizing? Am I minimizing? And it has to be one way. You cannot have two objectives realized at the same time. So you choose, what am I doing? Am I, for example, maximizing the contribution like the profit? Or am I, say, minimizing something like the cost in the production, or even the transportation cost, or say any other cost that could be related to the business you are dealing with as a business person. So once you have noted what is your main goal, yeah, we now ask ourselves, do we have the decision variables? And decision variables basically, I've talked about an example here, which I wanted us to be able to understand the terms which are required that I use as just an illustration. 1, the decision variables are things that you don't know at the moment when you're solving the problem. And this will be the major question that you want to address. These are things that you would want to know. How many units should I be producing? Or how many units, for example, should be sold so that the profit can be like this, or you're able to, say, minimize something like the cost. So decision variables are the key items which you'll be asked to find in an exam or in a question. And you may hear of how many units of a particular commodity, let's say Y, should a particular person produce in order to maximize the benefit. So what are we producing? Those units are what we don't know at the moment, and that is what we are solving, and so we call them the decision variable. So the very first thing that you do, once you have noted that the problem is of a maximization or maybe of a minimization, you go straight into identifying your decision variables. You say, let X represent, for example, the number of units of a commodity, say, let's say Y or any other that could be produced in the farm. So that let this be is our key element, because those number of units are the ones that you now intend to find at the end of the time, and that to be constituting part of your major solution to the problem. So when you are solving that particular LP problem, you must have identified those decision variables. Then the other thing is, how do I do this? What are some of the resources provided? And these resources, because most of the times are not enough, we now talk about the scarce resources, which means they are posing what we call a threat to us. In economics, we say the resource being scarce, then it means it is constraining us from producing, say, a huge amount of a particular commodity. So the constraints, which we normally state, this is my decision variable, these are, or rather, this is actually my objective function. For you to be able to achieve that objective, for you to be able to achieve your goal, then there are some constraints that you need to highlight. And this is very, very important because it's the one that helps you now to write down your linear programming problem. I repeat, for you to be able to write well an LP problem, what are the requirements? Number one, you must know what it is that you're doing. Are you maximizing or are you minimizing? And from the question, you can be able to detect. The problem talks about something like the cost, something like the contribution, or something like the profit, or even the revenue. So definitely, out of the guide, from the words that are coming from the problem, you can be able to tell what is the objective. And when you know that the objective is either of maximization or a minimization, you now ask yourself, what are the decision variables which I should have in my objective function, that at the end of the day, this is a question I'll address and say, these are the number of units to be produced for me to be able to maximize on my profit, or even to minimize on the cost. And then once you have noted the decision variables are this, it is now possible to write down that particular objective function. But for us to achieve that objective, then we are constrained. The question is, our objective function is subject to what? And now you write down those particular constraints. And I've said constraints are normally defined out of the resources which will be available as you, for example, try to achieve your objective. In a question of, say, maximization, the constraints are normally indicated in form of the less than or equals to sign. I repeat, if the question is on maximization, the constraints takes the form of inequalities, and that are in form of less than or equals to sign. In case the problem is of a minimization, then we are aiming at minimizing the cost, so the cost can be as high as possible. So we narrow down our case onto the lower edge, but we can be able to still have a higher cost incurred in the business. But because we are aiming at minimizing, then the constraints are normally defined in the form of inequalities, taking the shape of the greater than or equals to sign. So far, I've not given you an example on a cost minimization as an LP problem. I'll do that. What I've started with the cases of the maximization problems. And then other things are about these particular assumptions, which say, for example, the period to which we are to handle our case, that LP, the objective function is going to apply for a certain period of time, which we say those decision variables are going to remain static or maybe unchanged. So I want you to go through the other portion of the assumptions. But basically, I've talked about the key elements that we need to look at when we are formulating the linear programming problem. At the end of the day, once you have achieved your objective, you'd want to do what we normally call what if analysis. What if I were to increase this or I were to reduce this? And this is what we normally call the sensitivity analysis. We'll see it alongside maybe an example as we say this is a question where we involve maybe the sensitivity analysis. Once we have noted that we have got two decision variables, let's assume one to be plotted on the y, another one to be plotted on the x. How then can we solve a linear programming problem? There are two basic methods that we can go for. One is what we call the graphical method, and for one to draw a graph, you cannot deal with more than two variables. As I say, a graph will always relate one element on the y against another on the x-axis. Okay. Then we also have the simplex method. And the simplex method can handle even more than 2 variables, although in many scenarios you see decision variables are just but 2. This is a method where we call it iterative, meaning we keep on repeating some stages that we had already gone through until we find a solution that is actually optimal. We may not be able to understand. You can see what we already have here as the steps to follow up to until maybe we go through an example. But basically, when I put these 3 points, they may seem to be small, but it's a lot of work that one needs to go by until you can have that what we call an optimal solution to the problem. Allow me to look at one of the examples that I had already given you out earlier on. So that at least we can understand, because when I gave out this, I saw some are asking, how comes we have this and not this other one, or where are the figures coming from? I know you have your past papers. You can check on the question, the May 2018 example. It's a very important example which will help us maybe to just have a quick evaluation of what an LP problem is all about. So just go through the problem quickly. May 2018, question number 4C. Good, I've seen it. And I'm reading through the question so that we capture our major elements or the key items required for us to be able to go through the problem. And I read through the problem as follows. A farm manufactures 2 products, that is X and Y. So the products to be produced here are X and Y, subject to constraints on 3 raw materials, namely LM1, LM2, and LM3. The objective of the function farm is to select a product mix that will maximize weekly profit. So you hear of what is that the farm wants to do, and basically that helps you to pick out your objective, which is on maximization. Each unit of product X earns a profit of shillings 2, whereas that of Y earns a profit of 1 shilling. The details of the raw materials required for the production of the 2 products are as below. You can see the raw materials plus their maximum availability, and there are some units required for us to be able to produce a unit of, say, X, a unit of Y out of the available materials. So this particular example, before we go into solving it, whichever the method that is being required from the problem, you can't solve it if you don't have the problem itself. So number 1, do you know what we are doing? From the various steps we have talked about, understand the objective of the farm. The farm is aiming at maximizing. So once we have maximized, then the question is, what will give us that particular function? So with me, I've outlined the 2 products which are here. You can see them from my screen, the products X and Y. But that is not what we want to produce. The question is about us coming up with a product mix. The question is about us knowing how many units of product X should we produce, how many units of product Y should we produce also. And that's why in my starting of the question I've noted, let the units of product X be like this. I've just said let them be X. let the units of y be like this. I've also said let them be y units. So number one, I've already defined my decision variables. So my decision variables are these two variables here. These two here are the ones that we can now call decision variables. These are the decision variables. They are the questions, they are the unknowns. What are we going to, for example, produce at the end of the day? How many units? And this is what will finally help us to solve the problem at the end of the time. So once we have noted our decision variables, which are the x units and the y units, we want now to ask ourselves, how do we write down our objective function? The objective function, I've said, let my profit be Z. You can assume it to be any other letter. It's only that most books, they go for Y. Otherwise, you can write it to be anything else. So I've said, let my profit be denoted by Z. So this is what I'm calling the objective function. My aim being on maximization, and I'll say 2 shilling to be the contribution made by a unit of X, and 1 shilling to be the contribution made by a unit of Y. So at the end of the day, if I sell, let's say 5 units of X, I can tell how much will be the total profit of X. If I sell, let's say 20 units of Y, I can also say this is the amount I've gotten as a profit from Y. So in total for the two products, how much will be the profit generated and the highest profit in this case. But now for us to produce these units of X and Y, which are not known for now, we are constrained. And the constraints are the resources provided, which are the raw materials, that is, namely from the 3 LMs provided in the question. So I've picked the units. For us to produce a unit of X, we require 3 units of raw material, LM1. For us to produce a unit of Y, we don't require any amount of LM1 material. So we can formulate an equation and say, or rather an equality, because the aim is on maximization, remember, the inequalities are of less than or equals to signs. So I've stated 3x plus 0y less than or equals to 27, because 27 is the amount to which we cannot actually go beyond, because this is the only available amount of material M1. Again, from the coefficients given there, I've picked 0 units of LM2 to be the amount required for us to produce a unit of X, and 2 units of the same material required for us to produce a unit of Y. So again, you can formulate an equation, but again, we cannot exhaust or rather go beyond the available amount, which are the 30 units of material M2. And lastly, a unit of X will require 1 unit of material M3, and the same for Y. So again, with the 20 units provided, we cannot go beyond a third. Remember, our decision variables, we had said, these are the X and the Y units, which we had already stated, and let this be at the beginning. So at no point should you produce some units in your farm and then you end up having a negative amount of production. There has to be some units. They can maybe not be there, say 0 units, but we can never have a negative value. And that is why one of the assumptions we lay out in the linear programming, decision variables can never be negative. We normally say the last statement as you are formulating your LP problem is to actually write down the non-negativity element of your decision variables in the problem. And now, after we have, and you can see I've written 2 versions of my problem, because you can either write the 0 here, or even assume it. So these 2 actually have got the same meaning at the end of the day. Now, once you have formulated the LP, because our case we are dealing with only two variables, the x and the y units, it's possible that we can solve it either through the graphical method or even using the simplex method. For today's session, I just want to touch on the graphical method. Then maybe tomorrow or another day that you'll agree, we can look at the simplex method. So the graphical method, I've stated here, it is possible for us to solve this problem using the graph because I only have two variables, one to be plotted on the y and another one to be plotted on the x-axis. And I've stated, let the x units to be plotted on the x-axis and those of the y to be plotted on the y-axis. It's not a claim if you interchange the axis, only that you have to be careful on where you are putting whichever the amount you want to represent. If you say the y product to be on the y, to be on the x, it's okay, but you be careful when you're now doing your interpretation. Now, when we are drawing graphical representation, you cannot draw when you have inequalities. So the first thing you do is to actually assume. I've said we are assuming. You can see here, I've talked about the assumption, yeah? You can see what I'm trying to circle. We are not changing, we are just assuming. You assume that your inequalities, which are representing the constraints in the problem, are actually like equations. So the normal way into which you plot an equation on a graph, you do it as guided by that particular inequality. So in your mind, you'll be seeing an equation, but you're still remembering that this was actually a constraint to be indicated in form of an inequality. So once you have already assumed that your inequalities are like equations, you now go straight into plotting them into a graph. So you can start with any line. For example, I started with the first one where I had an equality of the kind. If I take you back, I had an equality of the kind 3x plus 0y less than or equivalent to 27, which we can still interpret as 3x less than or equivalent to 27. So now assuming that it is an equation, we just say 3x is equals to 27, and you can see there we only have x to find, which in this case is coming to 9. The same goes to the second inequality, which was of the kind 0x plus 2y less than or equivalent to 30. So it's the same interpretation as 2y less than or equivalent to 30. Assuming an equation again, we are finding the value of y, which in this case comes to 15. And then we had an equality of the kind, if you remember, x plus y less than or equivalent to 20. And by now, assuming this is an equation, you find the coordinates of x and y at the 2 points. Now, any equation that has only x, it will be a vertical straight line, and an equation that has only y, it will be a horizontal straight line coming from the graphical representation. Why I like solving my points or looking for the coordinates in just two ways, assuming an x of 0 and assuming a y of 0, it's because for you to draw a straight line, how many points do you require? You can have as many as possible, but basically 2 points are enough for you to draw a straight line. So you don't have to struggle, like assuming here x is 7, and then you try to find what is y. X is equals to 0. You don't have to complicate your work. These two are just but enough for you to draw a straight line. The only thing you require is a good ruler, so that when you're drawing the straight line, it will not be curving itself along the way. So after I had the points, I came into the illustration of my graphical work. Hope that we can see this, or you can still refer to the document I'd sent you earlier. So I've drawn my first line, which is an x of equivalent to 9, which we have said it's a vertical. Because the inequality was of the kind less than or equals to, then we shade the upper part. That is not required. the equation of the kind y is equals to 15, since the inequality was of the less than or equals to, so anything greater than that, again, we discard it. And again, we had the equation x plus y less than or equivalent to 20. Again, we are shading the upper part. So there are two ways into which one can decide. Do I shade my feasible region, or do I shade the unfeasible region? For me, I like shading what I don't want, so that when I'm discarding, I not interfere with what I want. And so I'm left with this particular unshaded region as my required region, which upon it, I can now come in and find the solution to the problem. The problem was on maximization. So what we are going to do here, we are going to be guided by the corner points. So I've picked the unshaded region, which I'm calling the feasible region. And this particular region, you can see it's not a well-defined shape. So you have to be very careful on how you pick your corners. I've picked corner A, corner B, corner C here, D, and even E. And as I am picking these particular corners, I want now to evaluate how much will be the value of Z. At point A, which has the coordinate 0, 0, of course, when we substitute the values of x and y in our equation, you realize that the value of Z will also be 0. Then for corner B, which is here, this one you don't have to calculate. It's definite that you can be able to read straight from the diagram what are the coordinates. X is equivalent to 0, y is equivalent to 15. And then again, you come and substitute, which gives you a value of 15 shilling as your value of Z. And remember, Z was your objective. So you still compare with another point if it's there in the problem. So I've started with E because this one I don't have to debate. The coordinates are clear from the diagram. X is equivalent to 9, whereas the value of y is equivalent to 0. And by substituting, then you find that our Z value is equivalent to 18. But now I am not using a graphical paper to be able to tell exactly where my point C is or my D point is. So if you are not clear on which are the coordinates of those points, I've given you a direction on what to do. For example, point C, which is a point of intersection between the two lines. One is y is equals to 15, the other one is x plus y is equals to 20. You can do the substitution of the y known in the other equation, and so you find the correct coordinates. And that is what I've done to be very careful that I'll end up getting the correct coordinates of the variables x and y before I do the substitution. Then again, at the point D, which I may not be able to tell exactly, like when I was drawing, you see one cannot be able to exactly estimate, yeah? Yes, it's slightly higher than 10, less than 12, but you cannot tell exactly where it is. So again, you can do the substitution of, let's say, x is equals to 9 in the equation x plus y where they are intersecting, and you again find the coordinates which are correct for your point number E. So you realize that when you are now substituting for the units, you now have different values of the Z, because the aim was on maximization. You now pick, do I pick 0, 15, 18? Do I pick 25? Or do I pick this other value, which is coming to what? 29. And in our case, 29 being the highest, it gives us the optimal value, with now the solutions to x units and the y units being 9 units as well as the 11 units respectively. So once we have noted what are our decision variables, which are the number of units of x and the y, we may go further, assuming our question is not ending there. We want to know, for example, what could be the binding constraints as well as the non-binding constraints. So what I've done, class, I have come back to my constraints, which were given as the amount of LM1, LM2, as well as LM3. And I've substituted the units of X and the Y in the various constraints that we had. And we ask ourselves, were we able to have exhausted those particular available resources? And if we don't have the exhaustion of the available resource, then we say there's a balance, and that balance is what we normally call a slack. Okay, and when we are reading the solution, for example, our solution is coming from where? From point number D. Using the graphical representation, let me go back to that. You realize that there are only two equations which are closing each other at point D. The other equation, which is y is equals to 15, it's not making any due contribution to point number D. So the constraints which are giving us point D are the ones we call binding constraints. And binding constraints are normally as per the resources which are usually exhausted in terms of the production at the decision variables that you'll have found their values for. I repeat, binding constraints are such constraints whose equations, when they are drawn on a graph, they'll contribute to a corner point that is your optimal point or your optimal solution. And these binding constraints, the resources themselves, which were actually scarce, that's why we are calling them constraints, they are normally exhausted. When we come in and we substitute the values of X was equivalent to X was 9 and Y was 11, if we were to substitute them in our two equations, you realize that we have got no balance out of the available resources that were given. And so they are contributing to the major solution of the problem. A non-binding constraint, like the equation y is equals to 15, which was representing the constraint, if you remember, 2y less than or equivalent to 30, that constraint will not have exhausted. If you are to substitute the value y in that particular constraint, you realize that you'll only have used y was 11, then you'll have used only 11 units of material LM2. And so we call this one a non-binding constraint. Now, binding constraints, because we have exhausted those resources, they do have what we call shadow prices, which are not zero. I'll come back to that. And the non-binding constraints, their shadow prices will always be equivalent to 0. We have only 1 minute, 2 minutes left. So I'll unmute you slightly before we are logged out, but you'll come back and you log in using the same credentials as we continue for another maybe few minutes. Let me unmute you. Okay, class, can you hear me?
Yes.
Yes.
Any concerns, so that when we come back, we'll log in again? We are about to be logged out. Any concern up to what I've talked about? Are you okay?
Yes.
Okay. So let me end this minute so that I'll be able to have time to convert my recording, and then you'll come back with the same credentials in a short while. Okay. So don't go away. We'll continue for another few minutes. Kindly. So when we come back, we'll talk about those constraints And I'll also help you to understand why we are saying they are exhausted, and maybe there's a balance onto some resources, or what we are calling the constraints. So when you come back, you'll wait for a few more minutes so that I convert my recording for his way of sharing. Usually takes a few minutes, so you'll wait a little bit.